Welcome everyone to this third day of the 6G Symposium. This is session one, which is dedicated to generative networks. So next-gen networks, are they GenAI networks? So we have three presentations today, one keynote and two presentations. The first speaker is Professor Mehdi Bennis. I have the feeling that you all know him, but anyway, I'm going to tell a few things about him. He's professor at the Center for Wireless Communication, University of Oulu, and a fellow and head of the Intelligent Connectivity and Network System Group, ICON, and has published more than 400 research papers. I have read them all. And he's been a recipient of several prestigious awards, including the 2015 Fred Ellersig Prize from the IEEE Communication Society and the Best Tutorial Prize in 2017. So thank you very much. The floor is yours.
Thank you, Miguel. Is it on, right? Yeah, very good. Well, good morning, everyone. Thanks for those who woke up this morning to come listen to my talk. So this talk, as you can see, will be about a very exciting topic called semantic communication. Means different things to different people. I'll give you my take on it. It's a work in progress. It's a lot of stuff. So let's see. So let's dive right into it. So state of affairs of 6G. So I'm going to be playing the devil's advocate, if you don't mind, today. So 6G promised a lot of things. Promised to connect physical, digital, biological worlds. However, the current visions, which we have seen since 2018, 19, more bits per second, more bandwidth, more small cell deployment, more backhaul, the better, are not sustainable, right? Taking 5G requirements and multiplying them by 10, 20, 1,000 don't make sense for many applications, such as robotics. You can ask KUKA. Taking 5G and adding AI and calling it a 6G, it's actually dangerous because AI today is really, as was said yesterday in the panel, hyped up, still brittle, energy hungry, just curve fitting at best. So you can, of course, take a look at all these numbers. I mean, you know them, take 5G, multiply by 10, 20, 50. Resiliency has been talked a lot during this conference, and I agree. It actually could be the new KPI in 6G. However, I ran a little poll on Twitter, not so official. I asked people, very high-level people from NSF rings, is resiliency in rings. Now you can see, for some it's reliability, for some it's dependability, for some it's robustness. It's none of those. Maybe I can come back to it at the end of my talk. In short, today, 6G is really nothing but an incremental evolution of 5G. I'm sure many of you agree. All right, so this is where I think we should maybe flip the current paradigm upside down and ask two questions. The first one is really, can we actually transmit less by thinking more? Humans do that all the time. We don't just spit stuff, right? If 6G is about human-machine collaboration and communication, which actually was the case, we said, okay, 6G, let me see, okay, let's connect machines now, robots, right? Well, then I think we have to look into ourselves. There is something very interesting there. So there's these two modes of cognition of humans. I don't know if you're familiar with them. System 1 versus System 2 by Daniel Kahneman, who passed away 2 weeks ago. And this is the framework even for AI, and I suggest this is the framework also for semantic communication and even for 6G. So System 1 is the one, the fast mode, the reflexive one. You have seen something before. It's like an Excel sheet. I have seen this environment before. I know what to do. I don't think about it, right? So it's pattern matching, statistics. Interpolate does not extrapolate. System 2 is the one we don't have in 6G. It's the one we don't have in robots. It's the one we don't have in AI, right? So don't be fooled by the AI hype again, right? And why? It's because, in fact, we need two things: planning, reasoning. Who does it? Us. Okay, so my thesis is all the work you see today in AI, semantic communication for sure, AI native, semantics native, whatever, 6G native maybe, fall under System 1. In fact, if you remove the word semantic, we have done them before. Anyways, so let's see. So we are actually at the cusp of two revolutions. The first one is, of course, the Pulse-Shannon, right? So some history is good here. So if you remember the paper of Claude Shannon, you have these three levels of communication: level A, level B, level C. Level A is, in fact, take X, encode it, redundancy, MIMO, this, that, and the receiver has to recreate X equals X hat. Shannon was very smart at that time, removed everything that humans need: meaning, structure, context, semantics, and so on and so forth, right? So just best encode, best reconstruct, and This is exactly where the requirement of 6G today come from. So with this logic, it makes sense, right? And of course, what's information in Shannon? We think Shannon information is really the only type of information. Well, not. Robots in a factory cannot use Shannon information to navigate and communicate. So there is a level B and level C, which in fact, even Shannon himself wrote a paper in 52 called the Bandwagon saying, do not use Shannon information, level A or technical level, for biological systems. So for me, a robot, communication between robots has to use level B, level C. So what's level B, level C? Well, this is a bit where the slippery slope of kind of semantic means, because it means different things to different people. Of course, we have to bring meaning, structure, memory, right? By the way, level B is send meaning, not data. So it's very convincing as an added value, right? And level C is act upon the meaning to solve a task, okay? But in fact, the way we like to look at it is what's really meaning, right? It's a philosophical topic, for sure, but from a more mathematical perspective, it's really about learning concepts, learning abstractions, learning what we call equivalence classes. This is compression 2.0, okay? And what's level C? Level C is, in fact, agents interacting in an environment, me reasoning about you, you reasoning about me, my intent, my goals, my beliefs, and we actuate each other. That's level C. Not what's written in that Shannon paper, which is very, very high level. Anyways, and also something we learned along the line now is we need everything to be closed loop system. So people who are working control theory understand this, us a little bit less. We need agency, dynamical closed loop systems, and information. This is also new to me, 3 years now. By the way, this topic exposes also the lack of knowledge, because we only familiar with one area of mathematics, statistics, but there are many other areas. So information here in this level B, level C is, think of it as information as a shape, as a topological invariant. A mug, a donut are equal, right? Why? They have one hole. This notion of information is not in level A. Okay, anyways, let's move on. So of course, everything is called semantic communication. Some people call it deep joint source channel coding, rate distortion, goal-oriented. It's a big mess. Likewise, for semantic information, is it the importance of data? Is it, so people working on age of information should know that. For them, the age of information is the semantics. Well, maybe for some cases, but it's very weak notion of information based on level A. Doesn't have any structure, right? Taking all your favorite AI models and just, calling that semantic representation is a bit dangerous, and I'll tell you why. Okay. However, there was a very interesting paper in 52 by somebody called Karnap and Barhilel. These are two gentlemen, where now they argue, in fact, we need to move away from the Shannon information, which is a scalar. Think of it as entropy of X, a value, 0.9. What do I do with 0.9? If I don't have the context, I cannot interpret it, right? So he came up with this set valued notion of information in a propositional Boolean logic. Okay, I would not go into details, obviously, in this talk, but just know that we go from a scalar to a set. What's coming after a set? A group. What's after a group? A category. So, the point being is we need structure. And the problem, we never talk about structure. So information as shape, I already mentioned this. We need to talk about information as structure, category, which is a collection of objects, right? And you have some, arrows, morphisms, we call them. That gives me a more precise way of describing information, because I can compose now. Semantic communication at heart is really about compositionality of concepts, maybe composing agents, maybe composing databases, whatever, okay? Anyways, and of course, we should not forget that we are not the only people working on this topic. There's a lot of work in logic. So people may be familiar with Kripke semantics from model logic. People in theoretical computer science do work on this every day, but do we interact with them? Probably not. So we have to a bit grow up in the sense of looking at different notions of information, different notions of quantifying semantics, and this is one of them. So this intention, I don't know, 3-4 years ago, I never heard about intention with an S. Intention with an S is really the semantic, the space where all the propositions, as in logic, live. And that's what you need in some applications. Anyways, let's move on. AI front, everybody knows, big hype, energy bill, sustainability, doesn't generalize. FL, federated learning, 5 years ago, I gave a talk on this. It's very popular, but that's not how you're gonna run your robots in a factory. Because they just do correlations. Again, they miss the elephant in the room, reasoning, planning, extrapolation, imagination, and all this stuff, right? So at least when we try to learn models, we need to add new ingredients. So everybody's familiar with these VAE, variational autoencoders, which are just some sort of compression, you can say, but they are missing this invariance to translation if you're an image, to a graph. If you permute the nodes, it's still a same label, right? Of course, those are symmetries. These are structures which we already know. We just bake it in the architecture. But can you discover symmetries from data? It's a big problem, right? Anyways, you have other desiderata here. I don't have time to go through this. The point being is really what we need to do, take data, break it down in terms of atomic elements here. These are the Lego. And then you piece back this Lego, do hypothesis testing, counterfactual reasoning. You know, this is exactly what AI is going to do. So in short, what you need to actually do is learning these semantic representations or collection of models, because we think we only live with one model. No, you have a collection of models. One is related to the other via self-supervision. We have to grow up and forget a little bit about supervised learning. It's not scalable. Wrong labels, who labels, how do you pay them? Again, what humans do, we always learn by self-supervision, at least when you are a baby, sensory motor. We touch, we break stuff, and then we build a model about that, and then later on language comes. So language comes very much after. Well, communication in 6G perhaps also comes after you have learned that structure of the world. All right, so I came up with this idea of really, because I was a bit confused, everything is semantic, but if I remove semantic, it's still the same stuff, you know, it's a bit confusing. So why don't we do system 1 versus system 2 semantic communication? This is the one we have today. If somebody asks me later, do we have semantic communication in 6G, blah, blah, blah? Yes, it's here, and I'll tell you why. This is the one we don't have today. This is the one where Yann Lequin wants to go for, Bengio, the AI gurus, which are ruling our world today, okay? Communication maybe just an application for them, who knows? Okay, so let's deconstruct unify. So I came up with this idea of system 1 semantic com. So let's look at it through the lens of, so you have this is a desiderata of the representations, so minimal, sufficient representation, VAE type of thing, latent representation. Also, the task is just a reconstruction task. In fact, it's like a level A type of philosophy as a communication. So maybe URLLC, EMBB application, semantic com maybe with just, okay, or data semantic, okay, I just focus on part of the screen. That's semantics. You have filtered away unnecessary part. Or maybe for AOI, you have a process here and you're interested only in the important stuff in your signal. Okay, that's semantic communication. Or maybe actually this was before even OpenAI was OpenAI. This was a Huawei keynote. You have an image of a dog. Okay, I don't communicate the dog. I don't communicate an image of the dog. I map a dog to a text, image to text, send a text, reconstruct the dog. Maybe okay, you want to fool us, okay, because you don't reconstruct the same dog. You generate a different dog. But this is very easy. Well, easy now. Maybe it was difficult back then. We looked at LLMs, in fact, also, exploratory work. These are system 1. All of them are system 1. Don't be fooled, right? So we played the Libby with Llama, Blip, mapping image to text, send the text instead of the image. Great, compression, nice. But you don't generalize, you don't understand so much what you do. You can publish papers, yeah, sure, but that's not the goal, right? In short, it's really about the fresher, the better, data filtering, and just perception. It's perceptual compression, nothing more. We need cognitive compression. Planning is cognitive compression, okay? Good. So system 2, in fact, is everything else we don't have. So you can look at it through the lens of this desiderata I told you before, or maybe better in terms of tasks. So now what I want to do, I want to compose different knowledge, piece them together, solve my task. I want to reason. You put me in a totally different environment, I can reuse my previous knowledge to solve that task, and so on and so forth. Imagination, digital twin, in fact, is just a projection of this topic, right? So for that, we can look at emerging protocols for collaborative robots in a factory. Open problem. Nobody can solve it. Okay? What's the vocabulary? What's the syntax? Is it 3GPP? Probably not, and it should not be. We also need to look at maybe even for telco type of problems, okay, can we learn new signalings? 3GPP doesn't like that. I like it. Okay? So I'll show you how we did it. Or here also, you have a teacher, a human talking to a robot, or the robot inferring me, I want coffee, so I don't have to really go to a coffee room. He understands my intent and go fetch it. You know, all these things cannot be solved without this. And of course, resiliency is absolutely related to this topic. Maybe some words on it later. In short, we need to have the abstractions, agency, dynamic of systems, so on. So let me walk you through some works. Some of them are old, actually, because we started, so it's been, again, a journey, right? A lot of lessons. This was the first work. We said, okay, let me take two agents, and I want them to immerse some sort of communication such that they have different beliefs about the world, and let's see what happens, okay? So we model this using what we call the triangle of meaning from psycholinguistics, which says that, so you have a referent, which is a dog. You see a dog, I don't want to, let's say, it's compression, so I don't want to, again, send the image, compress it, MPEG, JPEG, whatever. I want to abstract a concept, which is going to be this thought here, right? And then you symbolize the thought and send it to the receiver. That's actually what you see here. Speaker, listener, you have observational space, that's a raw data space. Concept meaning is here. So essentially, it's going to be a game between these two, the speaker and the listener, to converge to the same concept. That means we understood each other, okay? So in short, that's what we actually did here. We formulated it using statistics. Mistake, but it's fine back then. So again, can the listener infer the intent of the speaker? Okay, using his kind of Bayesian reasoning type of idea. Okay, and then we came up some kind of KPIs here just to calculate a bit, how often he can infer that intent and some trade-offs. Because at the end of the day, this is an instance of communication compute, because you have to reason about the other agents. So how many iterations I have to run in my brain before I talk to you? Should I talk to you every time? It's like, there's a latency communication trade-off. So mathematically, you can formulate it in a very neat way. This is essentially given here. This is a loss function. So this is the joint entropy between the speaker's context, mutual context. That's what they want to converge to, right? That's the entropy of P, and this is for the listener. So this is the loss function, which allows us now to kind of play a game between these two agents. Very clean expression. And of course, this is more kind of information theoretic aspect. So we can show, in fact, that by running this algorithm here, I'm not going to go through this, right? So this is the update of the mutual context equation. This is for the context of the speaker, and this is for the listener. You can see, show, prove, demonstrate that this converges to the same mutual context, okay? And then we have this alpha and beta here, which actually serve as a rate distortion in concept space. Because in fact, what's happening, if the agent abstracts too much, or storage gain or whatever, he can't talk to the other one. So you need to find it's like a dance between these two agents. Don't compress too much, and at the same time, you have to do it, right? So what's the right kind of trade-off, okay? So some special cases, I don't know, I'll skip this because I don't know what I'm doing with time. Terribly, as usual, but fine. So you can recover some very nice frameworks, in fact, called Optima Transport, for those who are a bit familiar with the area, which in fact is just, how do you, again, minimize the belief in the right space, obviously, between these two agents, and you can recover some very famous algorithms called sinkhole scaling. I'm going to skip this, okay? Okay, so just some results here. So we looked at this reliability as a function of many things. So these are the compression ratios, if you want, as a function of time. So self-iterations, how many iterations the agent has to run in his brain, right? So you can see here, a lot of things, in fact, that now this is an immersion process. So in fact, to have a higher reliability, you have really to wait maybe 200 time slot in your brain, right, before talking, right? So before you find the right alpha and beta. So faster convergence is not a good idea. Think, right? Our grandma says, turn your tongue maybe 7 times before you spit. That's a bit the idea here. We also looked at reliability as a function of number of communication rounds. So you can see the same trade-offs, in fact. So higher number of communication rounds, okay, higher reliability, but latency increases, okay? And maybe for those who like, I don't know, this is the payload size as a number of iteration steps for a system one. So system one is I send the raw data or I do some sort of compression using the image or text, right? And system two is really here. So you can see there's a huge gain. There's a huge gain, as expected, perhaps. Okay, good. The problem is, in fact, it's a kind of weak paper or work because, in fact, there are a lot of things missing. Machine learning, no machine learning actually in that, and it's point to point and many things. So what we realized, the step change in our brain was, in fact, it's all about structure. So let's look at a different type of structure coming from algebraic topology called simplicial complexes. I don't know if you guys are familiar with this stuff, but essentially what I'm going to be doing now is living in a space which is built by, vertex, edge, triangle, tetrahedron. Think of your data living in this space. And this is a very nice space because, in fact, I can use it to approximate any type of high-dimensional space. Okay? Of course, there's complexity there, but it's topological and algebraic, right? It's the topological, as you can see, right? Shapes and so on. And it's algebraic, I can compose. Take two triangles and so on and so forth. So when you do that, you have to ask yourself, how do I do signal processing on not sets, but on these simplices, right? So what's the convolution here? What's message passing here, right? So here you need to do some math, and then you have to look at different theories. Maybe some of you know this. I didn't know this 3 years ago. Hodge theory. In fact, what we will do is follow this mantra of structure and function. That's the brain. Brain deals with structure, function, and maybe a mapping between structure and functions, okay? We never talk about structure. We just do function, approximation, 1 billion data point, burn whole the forest of Finland, and we're happy. No, structure is important. So here we have to basically introduce some notations. So CK, this is the real valued function on a simplex. I'm going to be putting functions, data, information on vertex, edge, and so on and so forth. And I'm going to track the evolution because I want to learn is the intrinsic or the topological invariance of my data. That's what constitutes semantic information, okay? That's what I do here. I track them, you see here. This is a co-boundary operator. I know maybe some of you are not interested or familiar with this stuff, but that's how we do it. And then you calculate, in fact, this Laplacian. But this is a higher order Laplacian. You know Laplacian on graphs. But information never, or most of the time, does not live on an edge. Social network, you guys use social networks. Information typically lives in a very large graph, okay? That's the idea. Anyways, this is an expression of the order Laplacian, and then convolution is really run by this equation, which you give it a simplex C, and this is the Laplacian. This is the weight you have to learn. Let's go. Okay, this is just a picture of how this Laplacian works. And then what you do now, what you have to do, so you have a sender-receiver. So the sender has to now choose an order. What's my dimension? What's my K order here? And then you have to decide how many simplices I encode, how many do I send, and then the receiver has to decode two things, a topology, before it decodes the function. Because in fact, that's a trick. You can infer information if you have the structure. That's very easy. Okay, so that's actually what we did. So there's some result for you here. So what we actually did to show the gains, which works very good in terrible environments, low SNR, missing data, we distorted 50% of the data. And it still did work. So here we decode the feature, sorry, for the topology, right? This is the error, number of communication rounds. And then you have a trade-off between the order and the SNR. So you have to optimize these two, right? And once you do that, then you decode the feature, okay? Don't decode the feature before you decode the structure. In short, the impact of this type of ideas is actually very interesting as low SNR, I said to you. Syntactic error, no problem. In fact, even if I'm missing data from you, no problem. I can infer them. Of course, I have to know which order I am, which space, right? So the more structured, the better. I mean, that's the takeaway of semantic com in general. Okay, now let's switch gear. Let's talk about protocols. Very, very nice area. A bit, depending if in MBB. MBB is a bit difficult for 3GPP, but I mean, they don't want to compromise, but you can use it for other type of use cases. Okay, good. So we look at some very interesting ideas of learning generalized MAC protocol. Now I'm layer 2 via state abstraction. So abstraction is a word we should also start using. Actually, it's a very dangerous word to ask to define because it means different things to different people. But here, before we do that, so let's go back to this slide I showed you before. The System 1 MAC is exactly what Nokia Bell Labs. Good. So we said, okay, this must be a good topic because if industry has already started looking at it, then there is some good basis for that. So they took the 3GPP protocol and they said, guess what? Let's learn it entirely from data. Let's assume the teacher is a base station and the UE MAC learners are learners, okay? And they did it, but they did a mistake in the sense that they just threw at it, AI. So they used this idea of cooperative. They formulated it as a cooperative multi-agent reinforcement learning. And they use some techniques. I don't know. I don't want to go through this stuff, but I guess you're familiar with how Marl works. You have an agent, state, action, reward. Interact with the environment. The problem is, in fact, the same thing. Structure was missing, no invariant. Okay, they just work for 2 users, 4 users. It's kind of a joke, but it's fine. It's research. And the big mistake they made, it was a learning lesson for us. They learned a function. Not structure, a function from state space to action space. learn a lot of simulations, and impressive. I mean, you can show it works, but then you change the environment, you add 2 users, it fails. Okay. Point being, structure was missing. Okay, so we went exactly after that. So we said, okay, don't do this, do this. So don't learn a policy in the state space. Never. Take away today's talk. Learn it is this, call it information space, call it semantic space, call it whatever you want. And what's now this state abstraction is really up to you, kind of a menu. Is it based on cardinality of the set you want to compress? Is it based on the features you are interested in? Is it based on some more fancy stuff like some symmetries, in the environment, some invariants? So that's what we did. And it's very basically easy idea. We took a type of VAE type of architecture. What you see here, this is my observation. So I fed state, action, reward, full rollout to basically learn a latent representation from this state space, right? So I learned this Z, which allows me now I can do reconstruction, but I can generate different policies and different signalings and try them. Maybe do a mixture of experts, do whatever you want, test, okay? You have simulator, just test it, right? So that's actually what we did. Oh, sorry, yeah. And that's a bit loss function, the very basic stuff, because here what we have the expert policy, which is the teacher, which is the base station. So the users somehow just have to compress, they have to abstract so much so their states, which is the buffer state, channel state, to just match the expert policy, okay? But for us, we were happy to beat Nokia Labs. So this is basically what we did. I mean, total PDUs, the function of number of users. Our approach is here. You see it goes up. Their stuff is somewhere here. Yeah. It's a Q-learning approach, by the way, so it's not very smart, but anyways. So, it's much lower performance. And yeah, why? No abstraction, just call it this way. This is the same here, total number of PDUs per agent, same stuff. I mean, our approach is here. There, I think, is somewhere here, right? Yeah, Q-learning is here. Anyways, you know why. It's really abstraction. Okay, good. We also, because we are academics, right? 6G, we have to explore. So we looked at neurosymbolic protocols because we know actually inside us that living with neural protocols, the statistics is not enough. Why? We want to compress, we want to learn maybe more symbolic type of knowledge, can reuse, manipulate that graph to maybe test new hypotheses. Maybe this protocol is better than that one. So that's what we did, in fact. And yeah, we have a work actually appeared this year on JSAC. And one slide on it, sorry. So what we did, in fact, we took a neural protocol model, which we know this is like a generative protocol, okay? And these are 2 users, by the way, user 1, 2, uplink, downlink, base station. So what we did, we enrolled this, right? Because now what we want to do, we want to explore. It's a kind of brute force approach, so it's not smart. All the possible activities and expansions, so you end up with this messy graph here, and then we compress it. But everything is compression, right? No, but be careful. Here, what we want really is a kind of class of equivalence. We are finding trajectories. So my trajectory here is state, action, reward. That's my object, which I want to say, oh, this is the same as that one. So I'm doing some sort of clustering in the space of trajectories. And then you find this symbolic protocol model here, right? When you do this, when you compress, you get to ambiguity. So we get into this compression polysemy trade-off, meaning one symbol can mean many things, but you can solve that. You can solve that. Okay, and then we wrote this in terms of first order logic, so problog. That's what actually the first order syntax we use, and then we run simulations. There's nothing to prove here, unfortunately, but just to show you some visual, this is essentially this is a neural protocol model, and you can see here when you do this merging and this compression, you end up very, very, very good compression effect. Okay, that's uplink, that's downlink, and maybe just some results here. To show you, for example, if you compare both NPM and SPM for model storage and inference, is 10x, 100x gains. We compress so much, you can run it much faster. So good exercise, but it's 2 users, right? So it's a big problem. Anyways, good. Now let me get into even more fancy type of work, more math, but really high level. We wanted to take another use case, a semantic map discovery between 2 agents, or actually more, such that they can find a way to communicate based on their field of view and communicate, solve a task, okay? So how can the geometry of the data, which is going to be my semantic information, can be used to abstract, communicate better, robustly, and find a protocol which is robust, okay? Okay, let's go for it. So there's something called persistence diagram. I don't expect anybody to learn, maybe except some people in the group. But yeah, what did we do? This is a setting, agent A, agent B, field of view. This is like a road, original map, raw observations. And you can actually do what Nokia maybe may do. I should stop picking on Nokia. I like Nokia very much. A company X. So what they would do, they would throw at it again the same, but actually this is the same tool as before. It's kind of a 3 minutes, okay, plus. Okay, again, formulated as a pure MDP, partially observer MDP, give an action, space, which is to move in the world and to communicate. The problem, let me go fast forward here, no structure, no abstraction, nothing. Just, again, see, state, action, space. Okay, good. So we said, no, we can't do that. So what we did, same recipe, don't learn in state space, learn in information space. But what do we do now? We had to, again kind of use elements from algebraic topology. There is something called persistent diagrams. I'll show you how it works very fast. But just to tell you, in fact, that now you see, at least we have a very good grasp of what level B and level C. So for us now, we can say that the meaning of my data is really about this equivalence class of all the data that mean the same. Okay, compression. That's meaning for the agent. And of course, because we're dealing with symmetry and some group theory, we can actually capture that by orbits. There's something called orbits in group theory, which I'm sure all of you know. Okay, good. Anyway, so the approach is as follow. I take my, this is actually to capture a bit the field of view of the game. So step one, I need a quotient MDP. I want to compress my game or my problem. Because I know some symmetries, so I choose a subgroup, could be translation, rotation, whatnot. Here's a bit rotation, as you can see, right? So it gives you a class. You formulate this as a MDP with a group of G symmetries, which essentially says, again, how do I cluster the same trajectory because it's the same, just the rotation of the same trajectory, right? I do this. Step two, because symmetries are not enough, can I now add deformation? So we like deformation. Coffee mug, donut, deform is the same thing, right? Because one hole. So that's a bit the idea. So we did it. We called it reduce MDP. So how I'm going to find now these partitions? That's the problem. Let's see. So here we had to roll up our sleeves, look at something called, so there's something called homology and cohomology. But the nice thing there was really related to this notion of shape. So one more takeaway for you today. Not me, famous French mathematician said that when you use the word information, don't use it. Use the word shape, form. That's information. And actually, neuroscience agree 100%, not channel information. Channel information is like sampling one dot from that space. That's channel information. So what we did here, to pick your favorite data, point cloud, image, graph, time series, right? These are a bit the points here. And what we want to do is run this kind of process called the filtration, which is going to be able to track certain things. So this is, you see, there's a radius R, two balls intersect, boom. K equals 0 or 1, sorry, 1 edge, right? You see, and then at 0.8, oh, triangles emerge, great. 1.2, oh, tetrahedrons emerge, right? So you can see that you can encode this as a barcode, which is here. See, 0.6, some things die, some things born. So it's like about death and birth. Okay, or birth and death, which is very interesting for us. I'm going to skip this. We can see it here visually. If this is a field of view of the agent, another one here actually is the same. Same. Why? How do we measure them? In this PD space, persistent diagram or barcode space. This is just the noise. You see, you're born and you're dead. Okay, you're dead. I don't need you. Topological noise, topological noise, topological noise. I want this. I want to live early, to be born early and die late. Longevity. That's what I want to do. Anyway, this is in short what we did. Just some results here very fast here to show that it works. Of course, otherwise I would not have put it here. Very interesting. We can even prove that there's bounded loss when you do all this fancy compression. Very, very interesting. What's next? I will abuse of my time a bit, right? If I may. Because now it's getting even more exciting. So what's missing? What's next? So actually today, right now, we know how to do system one things. I like to use the brain, so we can do perception very well. We can do model-free, abstraction, but we are missing a significant element called planning, reasoning. If you check Financial Times yesterday, there's a guy called Yann Lequin. He's all over the place. You're French, you should know who Yann Lequin is, right? So he's all over the place, and I'll tell you what he's telling us. You will realize it's a bit strange. But in short, what we are missing, yes, is a world model. World model, new buzzword in the alphabet of soup alphabet, world models. Which is actually, yes, you need to internally simulate the world before you communicate. That's what we don't have. 6G completely lacks that. At best, is perception module at best. Anyways, so what we need is, so you need to learn a multi-model world model. Why? I just told you why. So imagine course of actions, choose the best one, run simulations before you take action. Good. So how do you do that? Well, thank you, Yann Lequin. Actually, he's very provocative, so it's good. We need those people in 6G. We don't have them. Maybe I can do that. So abandon generative AI. Maybe I should have been in the panel yesterday. Don't do generative AI for planning. If you want to generate high fidelity, stable diffusion image, yeah, go ahead, burn all the forests. It's good. But for planning, don't do that. Don't take X and Y and maybe compare them in the pixel space. What you should do, what he proposed, not me, is you need to now run these two X, Y, could be whatever you want, through encoder, and then you predict the semantic representation of X, of Y, sorry, from X, to operate in information space, in short, very basic stuff. He called it JEPA, Joint Embedding Predictive Architecture. That's him. So essentially what he just did, he just, guys, no. Representation learning is great. That's GenAI, everything you see around. Plus planning. Planning is a big deal, really the big deal. But he can't solve it, by the way, yet. And he looked at text, JEPA, image, JEPA, video, JEPA, but he knows, he doesn't say it, but we have to go towards multimodal, cross-modal, multi-scale JEPA. That's the brain, not Gianluca. I mean, Gianluca is just trying to rediscover a bit what we already know inside us. Anyways, so we looked at it in a very interesting work, actually collaboration with Bell Labs. We're applying this in a remote control problem, where essentially I want a base station remotely controlling a robot. See, frame K, frame class plus K plus 1. So we just applied the idea, in fact, here to learn first a JEPA representation, step 1. Once you do that, great stuff, because now the base station is relaxed. It can plan ahead, look ahead prediction, and maybe sample the robot image whenever it wants. Significant gains, you can see it a bit here. This is the prediction error, consecutive packet losses. So I can lose up to 5 packets, no problem. Packet error rate of 99.9999999. I guess it's a bit useless here, right? Good. So actually, I'm almost at the end of my talk. So I hope I convinced you today that system 1, system 2 is a very good compass to really know what's easy, what's not easy. Get out of the comfort zone. Most of us don't do that. I like maybe to do that. But in short, yes, we can do system 1 stuff. It just predict the next token, word, wireless channel, whatever. We just run this basic problem I told you, base station users, image text. It works. We published it, but if you don't have GPUs, you cannot run it. So Africa, developing country, global south, maybe it's a bit difficult, right? But we need anyways to go for adding these world models in LLMs. And it's not me talking, it's the LLM experts, okay? Good. One of my favorite topics should be yours too. This is 6G. We know how to do data fusion, to some data sensing fusion, yes, but we want to what? Fuse not the data. The semantic information of the data, which lives in different space. So to glue this information is actually a theoretical problem, first of all. And then you can do many things. You can, RF, image, LiDAR, radar, communicate. In short, this is an instance of semantic communication. Open problem. PhD students, this is what you should be doing. All right, my last slide. In closing, so semantic absolutely a game changer. Unfortunately, I hope I convinced you today, there's a big noise in the sense that, yeah, we think everything is semantic. Well, it's not. I try to convince you today. I like to look at it through this lens of system 1, system 2. I think it's very convincing. AI does it. Why don't we do it? And you know what? Difference between AI and communication is not that far, in fact. They're very close. Shannon used to do AI. Don't forget. We need agency. So you have to really study the problem from scratch, from an agency point of view, a dynamical control system. I sense, I perceive, collect my data, train a model. How do you verify the model works? Not ask a human to label it for you. You have to internally generate the data and match it with the real world. That's how it works. It's nothing new, actually, right? Information. It's not a dot. It's not a scalar. Shannon is a very tiny way. Well, we lived with it for decades. But it's invariant shape structures, right? This is 6G today at best, because I argue 6G doesn't do even active perception. It's supervised, a lot of data, train, no. Okay? So we have to rethink the whole thing through this lens. We need a calculus for compositionality. So compositionality, you think it's 1 + 1 = 2. Yes, that's linear algebra. That's high school. Guess what? Can you do the same as a space of shapes? Can I take a shape plus shape, add those shapes, and give me a new information? That's what we don't have. Of course, it's a super nice area of research. Okay, we don't do that. We don't care. Okay, and what else? Yeah, control loop. I told you. I want to compose now subsystems. I want to break down this whole network in terms of subsystems, connect them. Well, you guys call that interoperability, as far as I know. But here we can prove that's actually there's something called formal verification. I'm sure some of you know. That's the way. Actually, that's the way. Anyways, concept learning, so on. And back to resiliency before I close. Yes, resiliency, absolutely, guys. We have to work on it. You saw that it's not reliability. It's not robustness. Why? Well, one example. So reliability, we know it's terrible. It's a statistical measure. It answers one question. It answers the question is, I need to transmit a packet, is it 32 bytes, and the latency, and add 17 nines. Kuka told Ericsson, Michael is there. No, I can afford to lose some packets. Don't worry, don't over provision your network. Robustness is actually, think of it as known and known. You know the problems, so you patch it. Channel uncertainty, whatever. But you're fragile because I changed. Can you now be robust here? No, sorry. So resilience is a different beast, right? It's about really the brain. So thank you. The brain. It's really about plastic. You need plastic networks which are able, yes, to bounce back. That's the resiliency in latent, right? To recoil, go back to the state. But yeah, we need something more. We need this kind of plasticity in the networks, right? With the functional adaptation. Because today, if I ask people here, they will just tell me, yeah, it's elastic. You hit me and I come back. I'm resilient. No, we can do better than that. 6G doesn't have it, 5G even less. Anyways, and of course you can anticipate disruptions and so on. There's even another concept, I don't know if you know, guys, from economics called anti-fragility. You harness resiliency or harm to grow, explore different states. That's when you go to the gym. Pump, you suffer, you grow muscles, you're more resilient. Okay, but just to tell you here that this is a bit what we have to look at. And with this, thank you very much. Maybe I'll leave you with this sentence from René Thom, bifurcation theory. Thank you very much.
Thank you.
How long? Is it good?
Just in time.
Oh, okay, wow.
Questions for the audience.
It's the record.
Okay, the first one actually is the
Bombardment's coming.
microphones are coming. Yes. Patrick.
Wow.
Thank you, Mehdi, for your really inspiring talk.
Okay.
Well done. So you started and ended your presentation to resilience, which I think is super, super important as well. But having said that, if you think about very complicated communication systems, if you think about new ways of transmitting information like semantic communication networks, wouldn't that be less resilient, more prone to spoofing and faking and manipulating the learning processes, etc.? So are they a little bit contradicting?
I don't see them. So you're talking about, so first two questions. So first, is semantic related to resiliency? Absolutely. In fact, in the work we did, this simplicially complex, in fact, by the sender being resilient and semantic communication is there is by learning the minimal yet sufficient structure inside the brain of the agent to speak. So semantic and resiliency go hand in hand. Now, from a security, jamming, spoofing type of things, it's not my area. I see semantic as actually solving the problem rather than the problem itself. But yeah, I don't know. I didn't think about this from this perspective, but I was asked the same question a few weeks ago. Yeah, somehow can you use semantic communication to hide, to conceal the information to a third-party spy, such that he doesn't decode the information? I think it's possible. I think in fact, there's many works on this, and there are different names. It's not called semantic communication, right? It's privacy-preserving, I think, coding, right? So coding is a subset of semantic communication, right? So it is possible, yeah. But resiliency is a bigger beast. It's a bigger beast, and it took me a while to realize the difference. I asked Rings people, Rings. That's what they have Rings too, maybe. They realized in Rings 1, nothing happened. I think, is there anybody from Rings here? I don't know. But I asked these guys, can you define resiliency for me? I did a nice poll. We saw the result. Completely ill understood. So somebody here should maybe take over.
I think one more fast question.
Yeah, sure, of course.
Tatu Koljonen, I have a mic. So
Yeah.
Aalto University. Very nice question, very nice presentation, especially as we heard on the first day that 6G is beyond communication. It's beyond the traditional communication. At that point, we were thinking of digital twins and non-human originating communication. You are expanding to the more human intent-based communications. But maybe in this vision that we had on Monday, that there are digital twins and other communicators than just humans. What is the intent of a digital twin or an AI? How do you transfer intents between that kind of objects? And should in fact this be done by your semantics? Should that be in fact developed within the AIs, the large language models, and those places that really would generate then the intents for different purposes? And maybe one question as a layman: do these large language models and AIs, do they have these semantic ontologies that you are proposing here? Because I have understood that they don't, but they still perform amazingly well.
Yeah.
And shouldn't they have their? And is the Google the world model that you wanted? Does Google have it? Because everybody feed every day lots of feeds into that. So
Okay, let me extract the semantics of your question. So yeah, when you put intent, so also I was confused when I heard digital twin. Yeah, I know what it means for Bosch. Okay, intent. Yes, now there's intent-based management. For me, what I like to really digest it through the lens I've shown today. No, yeah, I have 2 robots in a factory with sensors. Okay, they have to perceive the world, learn a compact representation, not a massive one. So we're talking about small brains here, not large brains. Not enough to talk, to communicate, to navigate, to avoid obstacles, to communicate with the agent. So there's a human now, also intent. They have to understand the intent. What is the human trying to tell me, and maybe solve it as a task, or split the task among multiple fleet of robots. And then what is the subtask we have to solve first? How do we communicate? And then kind of emerge this kind of solve the problem by emerging the solution from the sub solutions, right? But they need a world model. And here I don't mean a world model as of Google. Yeah, they can do it. They can burn all the forests of the world. No, I mean a compact. I didn't say it here. A small type of world model which is good enough for the robots to reason solve a task. Of course, you can now decouple that, put that huge brain in a centralized server, but then you have this latency issues and so on. So yes, LLM right now is system 1. However, there's a track going to system 2. There's RAG, RAG maybe, right? It's the vector databases and so on, right? The ability to prompt. So now I don't want to have world model. I'm going to prompt the server. Okay, what do I do if I am in this situation? Okay, do this. Okay, great. Engineering hacks. I don't want to do engineering hacks. You guys do it. I mean, industry, because you have to make money right now. I don't want to make money. I want to spend some more time, because all these LLM solutions will disappear in 2-3 years. What I can tell you, since you mentioned LLMs, maybe I might find the word, the right way to look for LLMs actually is through the lens of dynamical control loop system, not passive data, vacuum the web, learn models. No, it's not our battle even, but we need to change that. One way to change this is this. It's one of them. Maybe the others, yeah. Hope I answered the question.
Thank you. Next question for the coffee break.
Sure.
So let's move very fast to the next. It's there.
Oh, already. Thanks.
So our next speaker is Jun-sun Kim from the Seoul National University. And he's going to talk about the next for cellular networks in 6G. So the floor is yours.
Thank you. Thank you for introduction. Good morning. My name is Jun-sun Kim, a postdoctoral researcher at Seoul National University from South Korea. Actually, in this talk, Professor Kyung-won Lee is scheduled to make a presentation, but due to a sudden important schedule, he cannot come here. On his behalf, I will make the presentation. In this talk, I'm going to discuss what innovations are needed in cellular network architecture to support next generation services. This talk is titled with Cellular Network version 2 for 6G from a network computing perspective. First, let's look at the philosophy of this study. Suppose that you're the head of a research team and there is a project to work on. If you have to hire someone to carry out the project, which type of person would you hire, passive or active? I think most people would hire someone who is active, because active people tend to take initiative, seek solutions, and quickly take control of their situations. On the other hand, passive people tend to wait the situation until someone else pushes them into action. So, what about cellular networks? Passive or active? Traditional network architectures are passive. A cellular system passively provides networking performance based on sender's request. So even if there is a change in network conditions, the cellular system does not take appropriate action until the sender requests again. This nature of passive networking has limitations to supporting time-varying performance requirements of next-generation services. To handle the limitations, we propose a new network architecture that enables the cellular system to collect essential information and actively provides performance. We call it active networking or cellular network version 2. So this talk will discuss why the networking paradigm in cellular network architecture should evolve from passive networking to active networking to support 6G services. As you know, 6G is targeted to support advanced latency critical services, such as extended reality, mobile hologram, and digital twin, which provide immersive user experiences by blending virtual and physical worlds. However, there are many challenging issues expected in realizing the services. One of the most critical issues is the limited computing capability of mobile devices. The computing requirements are expected to grow even faster than the improvement of computing capability on mobile devices. As a result, mobile devices will be limited in their ability to perform enough computation. This limitation will seriously degrade the quality of services. To address this problem, it is inevitable to borrow computing power by offering compute-intensive tasks to remote cloud servers over a cellular network. The task offloading enables mobile devices with limited computing power to provide high quality of services. So connected computing over networks is the key for 6G services. However, this brings a new challenge of strictly ensuring networking performance to exchange offloading messages between the client and server in real time. This challenge let us raise a question. How can we enable performance-guaranteed networking to make computation appear to be performed locally? Traditionally, to guarantee network performance, cellular systems have passively provided the necessary performance based on sender's request. To do this, there is a need to exchange information related to service requirements and performance provision between senders and cellular networks. Recently, to make these interactions on demand, advanced application programming interfaces have been intensively developed from Camara and Nephew project by Linux Foundation and GSMA Open Gateway. And there is an architectural technique called network slicing that allocates a logically isolated virtual network tailored to the performance requested by the sender. To do this, the mobile device requests the network slice associated with the requirement from the cellular system through the API. And the cellular system will map the performance requirement to a 5G quality of service indicator and provide guaranteed QoS to the slice. Like this, network slicing is devised to provide guaranteed performance. Furthermore, to accommodate demanding requirements of 6G services, 6G is targeted to secure much more improved network performance, such as 1 Gbps of user experienced data rate and 0.1 millisecond of error latency. This vision provides cellular networks with the ability to satisfy the performance requirements of 6G services. Lastly, to provide appropriate performance for each service, there have been efforts to analyze and define the requirements of 6G services more precisely. These studies are expected to give guaranteed performance to the sender by notifying service requirements through the API whenever necessary in traditional network architecture. So, are we now ready to support 6G services? Unfortunately, no, because there is a problem of highly variable performance requirements that traditional network architecture cannot handle. To understand the problem, there is a need to look at operating response time. Basically, operating response time can be decomposed into 4 delays. First one is the processing delay of the client and the networking delay on the uplink and the processing delay of the server. Lastly, there is a networking delay on the downlink. To guarantee operating response time from the network perspective, cellular systems should be able to control networking delays at the application level. So, how can the operating response time be guaranteed? Let's see a simple example. Suppose that there is an operating task with a target delay of 20 milliseconds. Processing delays of the client and server have 2 and 8 milliseconds respectively. In this situation, the cellular system needs to determine delay budget for uplink and downlink, considering the processing delays. For example, 3 milliseconds for the uplink and 7 milliseconds for the downlink. Then, based on operating message sizes, as you can see, the cellular system should allocate data rates to deliver the message within the delay budget. In this example, for the uplink, a data rate of at least 27 megabps is needed to transmit a 10 kilobytes message within the 3 millisecond budget. In this way, to ensure operating response time, it is necessary to determine delay budget and data rate with essential information, especially processing delays and operating message sizes. However, there are challenging issues of highly variable processing delays and message sizes for each operating process. Typically, a service application can request various types of operating tasks. For example, VR image rendering, AR scene composition, and AI/ML inference in metaverse services. Depending on operating type, message size changes because different types of application data are exchanged between the server and client. In addition, the computational complexity of operating tasks also changes. In the case of ML inference, the server executes calculations with high computational complexity. As a result, most delays are caused by processing on the server. In the case of video processing, the server performs tasks with relatively low computational complexity. So it has a different delay distribution than the ML inference task. Furthermore, even for the same operating task, processing delays can vary greatly. The figure shows that processing delay is highly variable for each operating task that is indicated in method index of x-axis. The reason is that multiple servers may perform computations cooperatively according to a function chain. Each function has different computational complexity, and computing time for each function heavily depends on how many computing resources are allocated. Message sizes also can change even with the same task, especially video image rendering. In a high-resolution video streaming, the server transmits a video image as an operating response. As you can see in this example, application data sizes are large, many megabytes or more, and constantly changing. In actual video streaming, data sizes are different because of using different encoder, but it is certain that data size is highly dynamic. To handle these challenges, including those previously mentioned, there is a need for a way to adaptively guarantee a data rate that is dynamically demanded due to the time-varying processing delays and message sizes. To handle the challenges in traditional network architecture, senders should request highly dynamic performance requirements, but they cannot know variations in requirements due to the limited information. So it is inevitable that the client will overestimate by considering the maximum processing delay and message size, and then request over provisioning. As a result, the cellular system allocates much more resources than will actually be used. This resource of over-provisioning would keep operating response times within the target time, but there is a serious resource inefficiency problem. Of course, the client can underestimate the processing delays and message sizes to improve resource efficiency, but there is a much higher risk of delay violation. If so, how can the limitations be handled? To do this, we think cellular systems need to actively manage network performance while collecting essential information through close interactions with end hosts. We call this active networking. The workflow is follows. The cellular system orchestrates delay budgets using partial operating related information sent from the client and allocates radio resources to provide guaranteed data rate for delay budget bounds. Then a request message is delivered to the server, and after finishing computations, the sender advertises server-side information, including actual processing delay and response message sizes. Then the cellular system readjusts the delay budget and resource allocation. So if it works ideally, task operating is completed at the desired time without wasting resources, as shown in the figure. For this ideal operation, there are two design requirements: active interface framework to collect essential information, and active performance management to provide guaranteed performance. The active interface framework includes various types of interfaces for a network controller to interact with end-host, service orchestrator, and RAN nodes. The active performance management is responsible for providing guaranteed performance through delay budget orchestration, performance requirement analysis, and resource allocation. Based on the design requirements, we design a cellular network architecture for active networking. This architecture includes an active interface framework and an active performance management system. In addition, this figure shows how they are structured in the proposed architecture. In conclusion, we find the limitations of the traditional networking paradigm that passively provide performance depending on sender's requests in realizing 6G services. We identify the challenges and requirements in innovating cellular network architecture for 6G services. We are currently discussing how this architecture can be implemented on the top of Open RAN architecture. Okay, thank you for listening. That's for my presentation. Is there any question?
Okay, we have time maybe for one question.
Hi, many thanks for that. I mean, I get the idea in principle, but in the real world, won't you have firstly multiple servers being used by the client for different workloads in that application? You'll have different users requiring the network simultaneously, and you'll have other network elements that are also contended, like the backhaul. where you maybe have different performance characteristics on the fixed part of the network. So when you bring all that together, do you have a chance of doing this active performance management genuinely end to end in a multi-user, multi-server, multi-application world?
I'm sorry, could you rephrase your?
Yeah. I mean, I'm thinking about you might have a device, but it might have two applications running simultaneously. So maybe the device is a camera, but there are two applications on the server side, one doing video analytics and one being, I don't know, a monitoring desk for a human. And one of those applications is using UDP and one is using TCP, and they're fighting with each other, and the two applications don't talk to each other. The network doesn't know this. How do you manage that?
In the principle of active networking is the per flow control. So I think if there are many applications or flows, cellular systems can control each application and flows.
Maybe discuss over coffee. I think there's more network-aware applications, not application-aware networks.
So let's keep in the coffee and thank the speaker once again. Our next presenter is Sasu. So Sasu is the Dean of the Faculty of Science at the University of Helsinki, but luckily for us, he's also visiting professor at the University of Oulu. And I think all I'm going to say about him is that he had this very nice idea of how to use LLMs as an interconnect for 6G networks, and I think he's going to talk about that. Very interesting topic. Thank you.
Introduction. So good morning, everyone. Really great to see you all here. And let's wait that we get the slides up. But presentations have been excellent today, and we already heard about large language models a bit, and now we'll carry on with this topic. So I will talk about how could we incorporate LLMs into the 6G architecture, and where it would make sense, and what would be the, in a way, the possibilities there. Also, there are, of course, risks as well. And as we know, this technological landscape develops very fast. We have to also, when we look into the future, take into account this rapid pace of technology. And even this year, so we know today that LLMs are not that good at reasoning, but there is very strong indication that later we will see more capable LLMs already in a couple of months, I believe, that are able to do more reasoning. And we are building systems, so complex systems based on these elementary elements. So one LLM, you have a second LLM, you have something else, you create a system. So those are becoming quite powerful. So it really makes sense to ask how these can support us in telecoms, in networking. Can these even help us generate networks and generate applications over networks? That's a really exciting direction. So this work that I'm presenting, so it's very much starting from the 6G flagship, and we also have the 6G Finland national network that has been very supportive of this work and fostering discussions. And in a way, the background for our work is really the observation that much of the current deployments around data and AI, those are kind of centralized, logically centralized. And then we gather data to a cloud, we do the machine learning modeling, or whatever we want to do, and then we have some results, and then we use the results. But we then see that having more distribution makes sense in many cases. We have been for many, many years, I've been looking at for over 20 years how to do distributed sensing and data analysis and so on. So we see a lot of potential there. And we would like to tap into the data we have available at the devices, at the edges, in a secure, privacy-oriented manner. and that requires the distribution. So in a way, today we lack this machinery. That how do we do this distributed data gathering, model building, model usage, and so on. So we lack the orchestration, and we lacked, in a way, the interconnect design that would facilitate this orchestration. So that has been, in a way, a kind of motivation for us that, we need to have an interconnect for 6G for many things we want to do that would work with data, would work with, the inference requests, inference subscriptions, work with, creating models, model updates, and so on. So we need to facilitate this. And as we know, we have really many endpoints, so many different kinds of endpoints having different needs. So how do we accommodate this heterogeneity into the system? And that has been a very, very big challenge, actually. But now we have the LLMs as one new element that we can consider when we design interconnects, when we design orchestration systems, and so on. So this perhaps one takeaway from my side, that now we look at the LLMs, so they are capable of doing this kind of task decomposition. So we have a specification coming in, we decompose. We can do that in a kind of automatic manner. We have subtasks. We do model selection for this decomposition in a kind of recursive manner. We can do task execution. We select the best possible way to implement a subtask. Then we get the responses, and we, in a way, build up the picture of what has been done, what is still remaining, and then we complete the overall big grand challenge given to the system. That's how some of these modern LLM-based approaches work, and that's a very powerful approach. Then as a kind of added point, we can create tools. So we have a problem, we then understand the problem, we then generate a plan how to solve the problem with a tool. We need to generate the tool, we then create code or whatever instructions are needed to then realize this tool, and then we use the tool. And that's also a very powerful abstraction, and we see quite a lot of examples today that how LLMs, for example, have been used to create tools. They're very good at creating source code and doing many of these things. So that, in a way, is the scene setting, piece for us, in a way, that we have LLMs as kind of orchestrators, or helping to orchestrate tasks, and then also as tool creators and users. And then we get into this distributed environment in which we then using the orchestration, we then deploy applications that are based on these primitives, in a way, so that we have more and more of these models, various components at the edge, through the edge cloud continuum, being orchestrated to address our needs. And those are the needs of the customers, of people. And then we can articulate the needs in a kind of very expressive manner. So we have a specification, we can, even in natural language, we can specify that what kind of application we actually need, how it should work. And then the system provides that for us. And we haven't had this capability before. We couldn't, 5 years ago, even envision that we could do these things. So now, actually, we are kind of really able to approach this and actually implement this as well. We are not there yet, of course, and we are now looking into 6G and beyond. So there is a good time to kind of explore, work on these. But it's a very kind of exciting time, in a way, that we are actually building systems that can understand us and start to address our needs. And to this end, we have then worked on the AI Interconnect. We have worked on a white paper. We wrote a draft version of the white paper. You see the link here on the slide. AI Native Interconnect Framework is in the title. And we have been expanding the team. So many of you have been involved and contributing to this. So I would like to thank all for the comments, questions, discussion. And then we are now kind of in the finalization mode for the white paper. So we would want to release the final version soon, but there is still some work to be done. And of course, all ideas are still welcome. So we are looking at this. And the white paper aims to provide a comprehensive view that how LLMs can be used in the 6G context and what are the possibilities, what are the open questions. And we have many open questions here. And as you can see from the outline you see on the slide that there are many sections in the white paper, many different considerations that we need to take into account. And now very soon, I hope we can then release the final version, but now you can find the draft online. So it's there, please have a look and all comments are welcome. And really for us, I think this is an exploration. So we explore that, what we have today. And we do see that we have many of these models, AI models available, LLMs. We do distillation, we have smaller models, we distribute the models, we create pipelines around the models. So that's something that we see, and we believe that it will be in a way something that 6G needs to take into account. How can we use that for the benefit of the network and then for the benefit of the applications? And now here you see our interconnect design. So we have been trying to think that what would be a kind of general interconnect design accommodating the different needs here from the network and also from the applications. So you see that we have the AI interconnect covering the edge cloud continuum from the devices into the core network and beyond. And we have as crucial duties. So we have the selection of components, the models, their placement, so their execution, task coordination, then the communication and routing across the elements, and then also safeguards and audit trails. So we need to, of course, document everything we do and understand that things go well and nothing goes wrong. So quite a lot of components are needed also there. And in this way, we can then start to instrument the environment I have been envisioning in the talk. And this covers, of course, both control plane and then the user plane. And we see ORAN as a kind of important element here, that ORAN would help us to kind of push this kind of AI deeper into the network and go more for the real life cases. And as for the models, we envision many different models. So here you can see network architecture enablers, different specialized models, and then use case specific models at the top. That's a really very rapidly growing area, and there is a lot of value in the models. So we need to get to the data and then to create these models, and those are actually they're like currency in a way. So those will be very valuable, we believe this. And we would want to accommodate the creation of these models and their use in the 6G context. And then we have the interconnect, and there's really the kind of in a way this messaging part, and we have adopted to use publish subscribe so that we have requests, subscriptions coming in, we have content, publications coming in, and then we do the routing. And we can do the routing in kind of semantic dimension as well. We can use LLMs for that, and that seems to be a powerful abstraction that also that we didn't have before. We can do really content-based routing, we can do semantic routing, and that was very difficult in the past. I have been working for many years on that. And then, of course, we need to have a memory for the LLMs, memory state for the routing and for kind of ensuring that everything goes well. And then we have the UEs, the network elements, they then subscribe data, they subscribe inference, they publish data, publish inference results. They also subscribe learning capability as well. So the pub/sub in a way decoupling of the endpoints using this kind of semantic communications, and also in a way the use of LLM so that we kind of do the model selection placement. So this really accommodates a lot of decoupling for the endpoints, And we believe that this would really accommodate many of the envisioned applications that we have for 6G as well. So that's in a way the baseline for us, and we have certain design goals. So one is that we have really simple endpoints. They really have this very kind of simple API to use. Then we separate concerns so that we use this task and intent analysis and decomposition. As I've been explaining, that LLMs are really good at this kind of decomposition, so we use that to the fullest, and that's in a way this decoupling is the basis for the interconnection. Then we have also the selection, so we select the models we use. We also select the places, the location in which the models are used. So that's an optimization problem. And then that way we can address the efficiency aspect as well. And then, of course, what we would want to support is different kinds of network environments. So O-RAN, but also what other APIs, network APIs we could envision. And now one very important point also regarding the LLMs. So LLMs are really good also, it seems, to do API brokering. So we can in a way use this kind of interconnect system as a glue over the different APIs. We plug in a new API, we give it specification, we can automate the integration of that to the other parts of the system. And that, I think that's a really big value creator for these systems. That if we really can accommodate different APIs, and we can do this kind of API broker. And there are good examples of this already. For example, the Gorilla system from UCB. So that's a model that is able to do this kind of brokering of APIs and function calling as well. And now to this end, so we have been looking at this white paper that we have been together creating, and we have been also doing experiments. So we have created different experiments, also prototype implementations of the interconnect using LLMs. We have been using public LLMs and private LLMs. And we have been also creating a testbed design connecting Helsinki and Oulu as well. And at the top, you see the architecture in a way that we have been implementing. So we have publishers of content, also of inference results and models. Then we have subscribers on the right-hand side, subscribing inference. We have neural routers. We have implemented neural routers, which are able to take these subscriptions, work with those, use LLMs in the analysis, and then match, data match, content from the publishers to subscribers, have also inference as a built-in primitive that the network offers for the endpoints. So this we have implemented, and we have execution units that then run the AI components. And these can be, at the back end, using heavy lifting, so, NVIDIA GPUs, or they can be also embedded execution units. So we have the selection problem, that what are the models we need to use, how big are those, where we can execute those. And then we have even further questions that, how do we split the models? We can do split transformers, for example. So that then we go into very, kind of low-level details that how the AI machine really works. And there are many optimizations we can do. So that's something that we have been now experimenting with. And as I'm soon concluding, so I will present two very small demonstrators. So one is that we have been implementing this neural pub/sub for network slice management. So we do real-time monitoring of the channel quality indicator. We have an inference request from a subscriber, sort of mobile operator, to the network that we want to study this channel quality indicator from a number of network slices. So do this for me, and then let me know if something is kind of out of the order, and then give then recommendations what to do. We could even automate that then we have certain operations that will happen given the kind of the properties that we are monitoring. And here you can see the sequence diagram. So we get this network slice data coming to the router, the broker. We then do the LLM inference if necessary. So there are trigger conditions. Those can be also LLMs which trigger actions. And then we notify the operator if it's needed. And here you see the prompts being used. So system prompt and then the user prompt. And we accommodate multimodal subscriptions as well. And then there's the decomposition as well, so that we can have really complex activities being supported. So we can really automate quite a lot of the application, where we offload application functionality to the network so that it's distributed and optimized. And here you see screenshots from our implementation. So we have the neural router, we set it up. We then have the network operator subscribing in a way what is needed. So the slice updates and analysis, and then the recommendations, for example. And then we have the network slices producing data. And then we have in a way the trigger conditions, then the analysis. And then we use GPT 3.5, I believe here, but we can use any kind of standard LLM, local or then cloud-based. And then finally we have the report going to the operator, and then we have subsequent action based on the report, and that can be also automated, as we know. So that's one demonstrator we have created, and then before concluding, another one is the neural router. So we have created, I believe, this probably the world's first neural publish subscribe router system based on LLMs, so that we are able to accommodate natural language or multimodal these kinds of subscriptions, which we then accommodate in a routing table. We do aggregation for the routing table, and then we use one or more LLMs to match incoming publications, so content, against the routing table, and then deliver the content, the information flows forward. And we have been looking at the optimization. So how would you optimize such LLM-based router systems? And the results are encouraging in a way that we can do a lot in terms of the efficiency improvements. And that's one building block for our interconnect. We need to do this kind of routing and reasoning of what we have from the subscribers and then publishers. But now I will conclude for now. Thank you very much for being here, and we'll be very, very nice to answer any comments and questions. Thank you.
Thank you. Maybe we have time for a couple of questions.
Yeah, thank you, Sasu, for a good presentation. Could you expand more about how do you see it in the commercial side and moving forward with commercial systems in the way you describe and the related IPR ownership?
Thank you. So that's a really good question. So I see that these developments, they enable a lot of new value, and the value comes from this kind of, in a way, the interconnection capability, that we connect not only now endpoints, but we connect also in terms of the APIs and content, and that's something that is new, and this kind of system integration will go to a new level, and it will open up a lot of potential in terms of revenues, I believe. So maybe that's one observation, and of course 6G as a kind of communication primitive, so it can really do a lot here in terms of the APIs as well. I think that's a huge possibility, and the in-network capabilities are also I think creating new value. But of course we have to go then into the details at what are the segments and what's happening there. But at least personally, I think there is a lot of potential. And in terms of the IP, so yes, of course, so we need to look at this and that's an important direction. Yeah, thanks.
Maybe we can take one more.
Arno Pärssinen from University of Oulu, and Sorry, Sasu, that I need to address this question now to you. This is probably more broadly to the whole society, and with my very limited personal experience yet on these things, everybody is saying that this is going to take a huge amount of computing resources. For me, it's always energy. And while you are speaking about unlimited opportunities, based on what I'm hearing from my hardware community, I'm not a computing expert, but what people are solving in microelectronics side is really that how to make that processing. And kind of the prediction is that if we go easily like this, the limitation is not about our imagination. Limitation finally comes because it takes all energy available in the world. That's what I heard in February at ISSCC. And we are starting to speak about as scarce resource then as we are having in the spectrum. So how we can address that early on? Who is allowed to do that? And are you monitoring with your ideas all the time what it really means? What is the cost? What is the energy? Is this sustainable? And I'm hearing a very little discussion on this. I start to be worried because these two communities are giving a bit different words. But I think that this is one of the things that needs to be solved upfront before we are there. And do you have a perspective on this? How we should be addressing it? Sorry, this is a very difficult question.
Thank you very much. That's a really, I think it's a great question, and we should be really exploring this. It's a very complex question, of course. So maybe a couple of points here. So yes, so these bigger models, they require really a lot of compute to build, really, hundreds of thousands of GPUs, and that takes a lot of electricity. But I guess maybe we don't need to do that very often. So maybe we need to do it just, very rarely, and maybe only a very few companies will do that in any case. So it's a kind of very kind of exclusive operation. How do you create a big foundation model? But then once you have done that, and it's good, then you can do distillation. So you create from a known good model, you create smaller versions, you do fine tuning, you optimize, and we see that the community is really good at this. We see amazing things being done on very small LLMs already. So I'm kind of optimistic that, yeah, so we are still exploring, but then kind of later on, so we will have many models of different kinds. They're optimized, fine-tuned, and the optimizations, they would be really good. So that once we know what we are doing, so then it becomes quite efficient. And then we get to this lower use of the electricity, and we can also run these on mobile phones. We can run the models on embedded devices. We're already doing that, but we can do that in a very efficient manner. So and if you look at the progress in 1 year, you look at the progress, what has happened. So today you can run on your MacBook, you can run pretty big open source LLMs, and you couldn't do that a couple of years ago. So that's tremendous progress. The distillation, quantization, all this knowledge, and we are only at the start here. So I expect that there are many things, very significant improvements coming up now in the next couple of years. So in a way, I'm optimistic, and you're very right. Sustainability is key, and of course the interconnect designs I mentioned. So those are important, so that we are able to select the best possible components, models, and place those in the best possible locations, so that we optimize the energy use and maximize the sustainability properties. So that's a short answer, but let's discuss more. Thank you.
Thank you all. So thanks the speaker once again.
Thank you.
And so with this, we conclude the session. Let's go for coffee now and be here at